Greetings! You are watching the second lecture on the course Introduction to Fourier Analysis. On this lecture we will concentrate on functions defined on Rd and which are 2π periodic in all variables. This means that if you fix a vector x1 through to xd in Rd and you add 2π to any of the individual variables, then the value of the function at the new point is the same as the value of the function at the vector x1 through to xd. You may recall from the previous set of lectures that such functions have a chance of having a Fourier series expansion. And this was simply because every function who has a Fourier series expansion must be 2π periodic in all the variables. Before starting the lecture in earnest, I would like to tell you the contents in a nutshell. And now, if you don't understand all the words in this nutshell, then don't worry, because the whole point of the lecture will be then to open this nutshell. So, the main point of this lecture will be to show that the complex exponential functions, which already appeared in the previous lecture, form an orthonormal basis in the space L2. By the very definition of a basis, this means that every function in L2 can be represented as a linear combination of these basis vectors. And this statement is equivalent to saying that every function in L2 has a Fourier series expansion. That was the whole L2 theory of Fourier series in a nutshell. Before starting with the details, I would like to mention that the constant 2π in the 2π periodicity assumption is quite arbitrary. In other words, this constant could be replaced by any other constant. It is just the periodicity assumption which really matters. Periodic functions may have a Fourier series expansion, and to treat non-periodic functions you will need the Fourier integral. Fourier integrals will be discussed later on this course. Okay, let's get down to the details. We start with some notation. The letter capital T will denote the d-dimensional box of side length 2π centered at the origin. Note that the values of a 2π periodic function on Rd are completely determined by the values of the function on this box. However, choosing precisely this box is only a matter of convention. We might as well choose T to be any other box of side length 2π. If f is a function defined on T, we make the following notational convention. We denote the average integral of f over the box T by this slashed integral. The normalizing constant 2π to the power d is here the Lebesgue measure of the box T. Next, we define the spaces of 2π periodic LP functions. For this purpose, let p be an exponent between 1 and infinity. Then let f be a 2π periodic complex-valued Lebesgue measurable function on Rd. We define the LP norm of f as follows. In the case where p is strictly less than infinity, we define the LP norm of f to be the average integral of the absolute value of f to the power p, and then the whole thing still raised to the power 1 over p. If the exponent p is equal to infinity, this expression doesn't literally make sense, so in this case we define the LP norm of f to be the essential supremum over the box T of the absolute value of f. Now that we have defined the LP norms, we define the space LP of T to consist of those 2π periodic Lebesgue measurable functions defined on Rd so that the LP norm is finite. In this definition, the 2π periodicity assumption should be interpreted in a Lebesgue almost sure sense. I should make a warning to those of you who might have earlier seen the standard LP spaces LP-Rd. These standard LP spaces consist of all those functions defined on Rd whose absolute value to the power p is integrable. In contrast, in our definition of the LP T spaces, we are only integrating over the box T. This implies that the standard LP spaces are included in the LP T spaces, but the converse inclusion is not true. For example, the cosine and the sine functions belong to the LP T spaces for all exponents t between 1 and infinity, but the cosine and sine functions are not in LP of R when p is less than infinity. This is basically because all powers of the cosine and sine functions are integrable over the interval from -π to π, but they are not integrable over the whole real line. Let us then move to some further notation. The notation c of t will stand for all the continuous functions defined in Rd which are 2π periodic. Similarly, the notation ck of t will denote those k times continuously differentiable functions defined in Rd which are 2π periodic. We also define a special version of convolution for 2-pi periodic functions in L1. So let f and g be functions in L1 of t. We define the convolution of f and g at the point x to be the average integral over t of fy times g x minus y dy. One can check, and I will leave this as an exercise, that the convolution of two L1t functions is also in L1t, which in particular means that this convolution is also 2-pi periodic in all variables. As another exercise, the convolution operator is symmetric, so the convolution of f and g is the same as the convolution of g and f. Next, we record a property of the LP-T spaces, which is definitely not true for the standard LP-RD spaces. Because the Lebesgue measure of the box T is finite, the various LP-T spaces are included in each other in the following way. The space L infinity of T is contained in all of the other LP-T spaces, and more generally, if P and Q are exponents so that Q is bigger than P, then LQ of T is contained in LP of T. In particular, all of the LP-T spaces are included in L1 of T. For the purpose of this lecture, you should in particular keep in mind that L2 of T is contained in L1 of T. These inclusions can be verified by showing that the LP-T norms are in the following order. The L1 norm is bounded by the LP norm, is bounded by the LQ norm, is bounded by the L infinity norm whenever 1 is less than P is less than Q is less than infinity. All of these inequalities are easy consequences of Hölder's inequality, and they crucially use the fact that the Lebesgue measure of the box T is finite. These inequalities are not true for the standard LP norms, and in particular the space L2 of RD is not the subset of the space L1 of RD. This is in fact the key reason why Fourier analysis of 2-pi periodic functions is quite a bit easier than Fourier analysis of non-2-pi periodic functions. Next, I will briefly recall the notation associated with the complex exponentials. First, let me repeat this formula, which we already saw in the previous lecture. E to the power ix equals cosine x plus I sine of x for all real numbers x. There are a couple of easy but useful formulas to keep in mind. The first one is that the modulus of e to the power ix is identically equal to 1. This can be verified by using the definition of e to the power ix above and the definition of complex modulus. The complex modulus of e to the power ix equals the square root of cosine x squared plus sine x squared, and we have all learned in high school that cosine x squared plus sine x squared equals 1 identically. Another useful formula regarding e to the power ix is how to differentiate e to the power iax, where a is an arbitrary real number. The x derivative of e to the power iax equals ia times e to the power iax. This you can easily verify just by looking at what e to the power iax means. The next useful formula to keep in mind is that the complex conjugate of e to the power ix is equal to e to the power minus ix for all real numbers x. Finally, if n is an integer but n is not 0, then the integral from minus pi to pi of the function e to the power inx vanishes. Namely, if you look at the definition of e to the power inx, you find that the integral of this e to the power inx from minus pi to pi equals the integral of cosine nx from minus pi to pi plus I times the integral of sine nx from minus pi to pi. And both of these integrals on the right hand side vanish when n is an integer but when n is not 0. Of course, when n is equal to 0, then e to the power inx equals the function 1. And in this case, of course, the integral of e to the power inx over the interval from minus pi to pi equals the integral of 1 from minus pi to pi, which equals 2 pi, or in other words, the average integral of e to the power inx equals 1. Now we have covered all the basic or preliminary definitions and notations that we need, and we can start doing some Fourier analysis. Let us start with the definition of Fourier coefficients. Let p be any exponent between 1 and infinity, and let f in LP t. As we noted earlier, this in particular implies that f is in L1 of t. Now fix an integer d tuple, so in other words fix n in z to the power d. The Fourier coefficient of f with index n equals the average integral over t of e to the power minus in dot x fx dx. Since f is in L1 of t, this integral converges absolutely. The dot refers to the standard Euclidean dot product. The first natural question here is that what is the meaning of this Fourier coefficient with index n? The best way to look at it is that it's the L2 inner product of f with the complex exponential e to the power in dot x. In the sequel, this function x maps to e to the power in dot x will be abbreviated to en. This was already mentioned on the previous lecture, but the functions en are all 2π periodic functions. Let us next make precise this discussion about the L2 inner products. The L2 inner product of two functions f and g in L2 of t is defined as follows. We will use this bracket notation to signify the L2 inner product. The bracket of f and g equals the average integral over t of f times the complex conjugate of g. It follows immediately from the Cauchy-Schwarz inequality that this integral is absolutely convergent. If you haven't seen this definition before, then it's an exercise for you to check that the bracket indeed defines an inner product on the space L2 of t. Let us make two remarks on this definition. The first one is that the L2 norm of f that we defined a bit earlier is exactly the square root of the bracket of f with itself. And the second remark is that the Fourier coefficient of f with index n, which was the same as the average integral of fx times e to the power minus in dot x, is actually equal to the bracket of f with the function en. The next goal of the lecture, and in fact the main goal of the whole lecture, is to show that the complex exponential functions en form an orthonormal basis for L2 relative to the bracket inner product. But before proceeding with that, let's start by recalling what the basis means. So let H be a Hilbert space, for example this L2 of t, and let Ek be an arbitrary sequence of vectors in H. We say that the sequence Ek forms a basis for H if every element little h in H can be uniquely written as a convergent series of the form little h equals the sum of Ak Ek, where the Ak's are complex coefficients. By a convergent series I mean that the partial sums of this infinite series converge in the Hilbert space metric to the vector H. Furthermore, this countable sequence Ek is called orthonormal if the inner product between any two elements Ek and El equals 1 if k is equal to L and 0 if k is not equal to L. To be perfectly clear about this definition, I want to emphasize that the notions of a basis and an orthonormal sequence have a priori nothing to do with each other. For example, any single unit vector in a Hilbert space alone forms an orthonormal set, but typically not a basis. However, quite often one is interested in finding an orthonormal basis in a Hilbert space, which means finding a sequence which is a basis and an orthonormal sequence at the same time. The next lemma states that the complex exponential functions en when n ranges in the integer t tuples form an orthonormal sequence in the space L2 of t. But as I just said, this does not yet mean that the sequence would form a basis in L2 of t, although in fact it does, and this is what we will prove separately. Let us then prove the lemma. By the definition of an orthonormal sequence, we need to show that if em and en are two complex exponential functions, then the bracket between em and en equals 0 if m is not equal to n and 1 if m equals n. The proof of this equation is just a calculation. Fix two integer d tuples m and n. And let's denote the coordinates of m by m1 through to md and the coordinates of n by n1 through to nd. With this notation, the bracket between em and en is first the average integral over t of e to the power imx times the complex conjugate of e to the power inx dx. To make progress from here, we use one more useful formula for the complex exponentials, namely that e to the power ia plus b equals the product of e to the power ia times e to the power ib. If you haven't seen this formula before in basic complex analysis, you should check it as an exercise. In particular, e to the power I m dot x equals the product of the factors e to the power I mj xj. And similarly, the complex conjugate of e to the power I n dot x equals e to the power minus I n dot x, which further equals the product of the factors e to the power minus I nj xj. With these equations in hand, we see that the bracket of em and en equals, up to a normalizing constant, the product of the integrals from minus pi to pi e to the power I mj minus nj xj dxj. So, in order to calculate the bracket between em and en, it suffices to calculate separately these d one-dimensional integrals. Let's do this now. If m is not equal to n, then there exists at least one index j so that mj is not equal to nj. In this case, the integral from minus pi to pi of e to the power I mj minus nj xj dxj equals 0. This was one of the useful formulas for the complex exponentials, which we recorded on page 4 of these lecture notes. As a consequence, the whole product here equals 0, and hence the bracket between em and en also equals 0. On the other hand, if m is equal to n, then also mj is equal to nj for all indices j, and in this case mj minus nj equals 0, and the integral from minus pi to pi of e to the power I mj minus nj times xj dxj equals 2 pi. And then it follows that the bracket between em and en equals 2 pi to the power d, but then we also have this normalizing factor in here, so hence the final product is equal to 1. This completes the proof of the lemma. To summarize the progress so far, we have now shown that the sequence of complex exponential functions en when n ranges in the integer d-tuples forms an orthonormal sequence in L2 of t. But we haven't yet shown that this sequence would be a basis for L2 of t. Informally speaking, the issue here might be that there are too few of the functions en. For example, if there was only one function en, then definitely this sequence of one function would be an orthonormal sequence in L2, but it would be hopeless that this one function would span all of L2 of t. So the question becomes, how to show that the complex exponential functions also form an orthonormal basis in L2? There is a highly useful criterion from the abstract theory of Hilbert spaces when an orthonormal sequence is actually an orthonormal basis. I will next go through this criterion in detail, but I will not prove it because the proof is contained on the course Functional Analysis. So here is the criterion, it's lemma 1.8. Let H be an arbitrary Hilbert space, and let Ej be an orthonormal sequence in H. Then the following conditions are equivalent. The first condition is the one which we are actually interested in. Ej forms an orthonormal basis of H. The second equivalent condition states that every element h in H can be decomposed as follows. H equals the sum over the j's of the dot product of h with Ej times Ej. Now if H was the space L2 of t and the functions Ej were the complex exponentials, then this formula would exactly say that every function in L2 has a convergent Fourier series expansion. The third equivalent condition can be viewed as a generalization of the Pythagorean theorem. It states that for every element h in H, the norm squared of H equals the sum over J of the absolute value squared of the inner product between H and Ej. If this formula does not look familiar to you, stop the video right now and think what it says if big H is Rd and the Ej's are the standard basis vectors. This condition number 3 is quite often also known as the Plancherel identity. The fourth equivalent condition is often known as the Parseval identity. It states that for all elements h1 and h2 in H, the inner product between h1 and h2 can be expressed as the following sum over the indices j of the inner product h1 with Ej times the complex conjugate of the inner product of h2 with Ej. Once again, if this identity does not look familiar to you, try to think what it means when big H is Rd and the Ej's are the standard basis vectors. Finally, whereas condition number 1 was the property that we actually want to know, it is the equivalent property 5 that turns out to be the easiest to verify. It states that for all elements h in H, the inner product of H with all the vectors ej vanishes if and only if H is the zero element itself. As I already said earlier, this result is one of the core results on the course Functional Analysis. On this course, we will just apply the lemma to the orthonormal sequence formed by the complex exponentials. In this context, the lemma states that if we want to verify that these complex exponentials form a basis for L2, we only need to verify this condition number 5. In other words, if you have any function in L2 and the inner product with all of the complex exponentials vanishes, then the function itself must be 0. And that is precisely what we will verify in the next lecture. This concludes the second lecture on the course Introduction to Fourier Analysis. Thank you for watching and goodbye.